problem. Man seeks to produce two different kinds of freezers called A and B. Each of them must go through 3 operations before marketing, assembly, painting, and quality control. Freezers require, respectively, 2.5 and 3 hours of assembly, 3 and 0.6 kilograms painted enamel for 14 and 10 hours, and quality control. Total manufacturing costs per unit are respectively 30 and 28, and selling prices 52 and 48, all in 2 and 48, all in thousands of pesos. The businessman has 4,500 hours weekly assembly, 3,400 kilograms of enamel, and 20,000 hours for quality control. Market studies show that weekly demand freezers not exceed 1,700 units and, in particular, the Type A is at menos 600 units. Modeling. The decision variables are the number of freezers type A and B. The objective function represents the total benefit. The restrictions are due to the time available for assembly, enamel availability, time available for quality control, and demand for freezers. Method of the 2 phases. Phase 1. The problem is put in standard format, maximization adding a slack variable to each constraint, S1, S2, S3, S4, S5, and an artificial variable to the 5th restriction, R1. The associated table. Finding the first new row, Z, phase I of the problem is solved, which results in optimum following table. As the minimum, Z equals 0, phase 1, produces the basic feasible solution, S1 equals 3000, S2 equals 1600, S3 equals 11600, S4 equals 1100, and X1 equals 6600. At this point, the artificial variables already completed their mission, and can eliminate columns of the table and continue with phase 2. Phase 2. After removing artificial columns, write the original problem as shown in the following table associated with phase 2. According to the optimality condition, none of the coefficients of the Z-row are negative. Therefore, after 4 iterations reach the optimal tableau. Graphic method. For this method should be cleared the variables x1 and x2 in each restrictions. These values are then plotted to determine the feasible field, and then obtain the optimal solution. In both methods the optimal values of the variables are obtained, which are interpreted as follows. The utility is 346,8400 pesos. Manufacture 882 freezers type A. Manufacture 764 freezers type B. The values of the slack variables in the previous optimal solution are 3 hours of assembly time left over, 295.6 kilograms of enamel that are not consumed, the total of 34,000 kilograms, 12 hours of quality control left over, 54 are left freezers manufactured by the limit 1700, 282 freezer type A manufactured above the limit 600. Then, the solution is assemble and quality control. Changes in the availability of resources, right side of constraints. The number of hours of assembly moves parallel to itself its restriction to any point on the line segment, FD. The number of hours of quality control moves parallel to itself its restriction to any point on the line segment, BG. Changes in the utility unit or the unit cost, objective function coefficients. First, write the objective function in the general format. C1 may decrease 15714.2 and increase to 26,400, and C2 may decrease 16666.7 and increasing to 28,000. Shadow price. To calculate it, should divide the value change of Z in the feasible interval I, in resource feasible interval I. The value per unit of resource can also be calculated by converting a dual primal problem. Taking the last iteration of the primal problem, and the values of the objective function, is obtained. Sensitivity analysis and shadow price with solver. To resolve the problem through solver, must be set the values of the objective function, and constraints. Then multiply each of the values of the restrictions with the decision variables. Then Z, multiply each of the decision variables, with the objective function. Later, let's data, and then let's solver. After opening the window, diligence each of the fields. Select make unconstrained variables non-negative. In solving method we put simplex LP. In reports select confidentiality. There we can see the optimal solution for the variables x1 and x2, can also be seen in the objective function each of the ranges upper and lower, in which they can change the coefficients. These are 6,000 and 5,333.3 pesos for x1, and for x2, 6,400 and 4,285.7 pesos. In the same way we can see the range and shadow prices of assembly operations and quality control, which are the optimal solution. For assembly we can see that it can decrease 225 hours and increase to 231,48 hours, with a shadow price of 3529,4. For quality control can be decreased 666,7 hours and increase 1,600 hours, with a shadow price of 941,2. This shadow price, what we want to say is, that both will change the final value of the objective function, for each unit that increases or decreases the right side of the restriction, within their allowable ranges, increase and decrease.